As we create building models, we often specify elements using types that are composed of many layers. This is especially true of floors, walls, roofs, and even ceiling elements. While we often think of these elements as being single objects, we can explore the layers that make up their types by choosing to edit the type, then editing the structure, and looking at the specific materials and thicknesses that make up the structure of the element. For example, we can choose one of the exterior wall elements, edit the type, then edit the structure, and look at all the different layers and materials that are used when we create this wall element. Treating these multi-layer elements as single objects makes it very convenient for us to model, because as we make changes to the elements, the effect on all the individual layers is handled for us automatically. For example, if we open a floor plan view and choose to place a door element in our wall, the effect on all of the layers of the wall is handled automatically for us. The advantage of being able to work with these multi-layer elements as single objects is especially true when we consider objects with complex geometries. For example, sloping roofs, where making changes to each of the individual layers of the element would be especially difficult and time-consuming. While the convenience of using these multi-layer elements works very well for design modeling, it starts to break down a bit when we consider using BIM models for construction modeling. In particular, treating all of the layers as a single element creates inaccuracies for construction planning because the layers of the wall won't be assembled as a single unit. Typically, the structural layer will go up first, followed by the finished layers being applied at a different time, and also creates inaccuracies for quantity takeoffs, because the quantity of the materials for the layers at the inside of the wall are typically less than the quantities at the outside surface of the wall. And while this may be a small difference for a single wall across an entire building, this can add up to a significant difference. To make it easier to address both these needs, Revit 2012 introduced a new feature called Parts, which lets us break down multi-layer assemblies into individual parts so that we can edit, schedule, and work with them independently, while still adopting the changes made to the original element. Let's move to a simpler model where it'll be easier to see the effects of working with parts. In this model, we have a multi-layer wall, as well as a multi-layer floor, but the elements are modeled as single pieces. To break this wall element or floor element into parts, we select it, and then in the Modify Walls tab, go to the Create Parts tool. When you click Create Parts, and then click Away, you'll see that the individual layers of this multi-layer wall have now been separated, and we can work with them independently. Let's change the adjacent wall into parts also, and you'll see that Revit accurately models the intersections between the layers of the wall elements. Each view's settings now offers a parameter that lets you control parts visibility. You can choose to show the parts, the original elements, or both, depending upon what your needs are. For now, let's just show the parts so we can work with them easily. We can select individual parts, and when we do, notice that in the Properties palette, the volume, area, length, thickness, and height of the part are all reported, so we can get accurate quantities for that individual part as opposed to the entire wall element. We can reshape a part by turning on the Show Shape checkbox, and when we move into the model area, you'll see that shape handles appear on the part, which will allow us to stretch, push, and pull the individual part layer. We can also change the material associated with a specific part. By default, new parts are created with Material by Original turned on, so we can't edit the material for that part. But if we turn that off, we'll be able to edit the material and open the Materials dialog to choose a new one. One particularly nice feature of parts is that if we edit the original element, the parts will automatically adopt the changes we make to the original. To see that, let me switch back to showing the originals in this view, and I'll make a change to these windows. As opposed to having that be separated by 7 feet, let's make it only 4 feet. When I go back to showing the parts, you'll see that the parts that represent the layers of the wall have automatically been updated to reflect that new window location. So there's no disadvantage as a designer to working with parts, but for construction modeling, we get the advantage of being able to work with the parts independently so that we can more accurately model the true construction sequence. Another advantage to working with parts is that we can use them to model materials changes in specific areas without having to create new types for every small material change. A common example of that is floor elements. Rather than creating separate floor elements of different types to represent different areas where the finished floor material is going to change, we can convert the floor element into parts and then divide the parts to represent the different areas that will have different materials applied. Let's see how that's done. We'll start by selecting the floor element, then use the Create Parts tool to divide the floor into individual layers. We can now work with the layer representing the finished surface of the floor independently of the other layers. Let's reorient this view to make it easier to make changes to that part. We'll switch to the top. And now we can divide the part to separate it into different regions, applying different materials to each of those regions. Let's use the Divide Parts tool, and we'll enter a sketching mode, where we can draw lines that will separate the part into subparts, each of which can have its own separate material. For example, if we draw a line across the rear of the building, then say OK, we'll have one part representing the finished floor in the back of the building, and a separate part representing the finished floor at the front of the building. In the back of the building, we can select that part, turn off the Material by Original setting, and then choose a different material for the floor in that area, maybe tile. With a surface pattern that'll allow us to easily see the distinction. Click OK. And we now have tile in that back part of the building. And we'll now have a part that accurately represents the area and amount of tile for the rear portion of the building. Let's try something else. We'll again choose the part, then use the Divide Parts tool. This time we'll use the Rectangle tool and draw a division in the middle of the part. We can adjust this area to make it perfectly square. Say 14 by 14. Then we'll use the line drawing tool to subdivide that part into even smaller parts, using horizontal and vertical lines to ultimately create a checkerboard pattern. Note that when we're drawing lines to subdivide parts, the rules aren't nearly as restrictive as many other sketching modes. We're allowed to overlap lines and have them intersect. The only restriction is that the dividing line must truly separate the different part segments. Let's finish this. And now we can select each of these parts independently. We can select one, then Control-click to select the additional parts to make up a checkerboard pattern. Turn off the Material by Original checkbox, then choose an alternate material to make up the alternating segments of the pattern. For example, if we want to use the wood cherry as an alternate material, say OK. And you'll see now we have created the pattern on the floor without having to create separate floor elements. One of the key advantages of using parts when construction modeling is the improved accuracy you get when scheduling building elements and materials. Let's take a look at some typical schedule views to see the impact of using parts. Let's open a typical wall schedule that displays a list of the different wall elements in our project, as well as the areas for each of those wall elements. And you'll see that those elements are reported to have a total area of 989 square feet. An interesting question is, where is that square footage accurately measured? At the inside surface of the wall, at the exterior surface of the wall, or at the wall location line? If we look at a material takeoff schedule, we'll also see the inaccuracy there. In the material takeoff, all of the materials across the different building elements are aggregated by the material type, and you can see that the same material area is being reported for each of the different layers of the wall assembly. The gypsum wallboard layer on the inside surface and the masonry brick layer on the exterior surface are reported as having the same area, and this is inaccurate. Let's create some new schedules. Let's create some new schedules that work with the parts we've created to gauge the improvement in the accuracy that they provide. We'll open the View tab, choose Schedules, and start by creating a schedule of quantities. The quantity we're going to schedule is actually parts. We'll choose that. And the fields that we'll choose to show are the original category of the part, the material of the part, as well as the area of the part. We'll sort and group this first by original category, and then by material, and we'll add a blank line between the different categories to make the schedule easier to read. Finally, let's format this schedule. We'll choose the area, and right align that, and add a total so we can sum up the areas of all the individual parts. We'll say OK to display that schedule. It's looking a little messy now because it's showing each of the individual parts. Let me go back and remove every individual instance. Say OK. And now we'll get a much cleaner looking schedule, which just reports the total area for each of the different parts that are being used in the floor, as well as the parts that are being used in the wall elements. And you'll see that we're starting to see a difference. The masonry brick layer is using 992 square feet, whereas the gypsum wallboard is reported to be using 956 square feet. So we're seeing a significant improvement in the accuracy compared to the 989 square feet, which was reported for all the different layers using the standard schedule. We can also do a part-centric materials takeoff. Again, switching to the View tab, choosing the Schedule tool, and then choosing Material Takeoff. We'll choose Parts as the category to schedule. Say OK. And in this case, we'll again choose Original Category, but now we'll choose Material Name and Material Area. Again, the advantage of using the materials takeoff as opposed to a schedule of the building elements is that this will aggregate all the different materials across different categories of elements into a single schedule, as opposed to having to take them off as individual categories of elements. We'll switch over to sorting and grouping. Again, sort by original category and material name. We'll put a blank line footer underneath every original category to make that easier to read. We don't need to be seeing every instance again. Let's turn that off. And finally, we'll format this using right alignment and calculating a total on the material area. Say OK, and you'll see again we get a very similar schedule. This one reporting the materials that are being used by each of the different parts in the different categories of elements. And you'll see again that we're seeing a variation from 956 square feet at the interior surface all the way up to 992 square feet at the exterior surface, which is a much more accurate takeoff of the true quantities in our building model. Now, this may not seem like a big difference in this small model, but across a large building project, this difference can be very, very significant in the total figures that are being computed.